Hey there, my name is Gokul, and today I'm going to talk about how we can robustly handle diverse preferences in reinforcement learning from human feedback. RLHF is the problem of optimizing on the basis of relative preference feedback rather than absolute reward feedback, like in traditional reinforcement learning. For example, we might ask some human raters to rate prompt completions generated by our model, and then want to use this data to fine-tune our model to be a better conversationalist. The standard approach to RLHF is a two-stage procedure. First, one trains a classifier between the positive and negative samples, and then uses this classifier as a reward function from an arbitrary downstream RL procedure. One can also do this in an iterative fashion if they can query a teacher model in the loop for on-policy preference labels. However, reward-based approaches to RLHF suffer from a fundamental problem. They are not able to robustly handle a diversity of rater preferences. Consider a set of three subpopulations of raters, the first of which prefers rock to scissors and is fraction A of the population, the second of which prefers paper to rock and is fraction B of the population, and the third of which prefers scissor to paper and is fraction C of the population. A bit less impressionistically, we can represent each set of preferences as a matrix, where each element is the probability that the row is preferred to the column, rescaled to be between -1 and 1. As a result, these matrices will always be anti-symmetric. Now, if we aggregate these matrices together, we end up with the following set of intransitive preferences. Observe that there is no reward function that explains these preferences, as it would need to simultaneously set the reward for rock higher than that of scissors, paper higher than that of rock, and scissors higher than that of paper. Now, moving to the LLM setting, this problem only gets worse, as we have to choose from the space of all natural language completions to a prompt, and it's very unlikely that the majority of raters think a single string is preferable to all others. Okay, so what can we do about this? Thankfully, we can build upon techniques from the social choice theory literature on how to best aggregate preferences. Consider the policy pi star that plays 1/3 rock, 1/3 paper, and 1/3 scissors. Observe that samples from pi star are, with probably at least 1/2, preferred to samples from any other policy. More formally, this is known as a Nash equilibrium. In the social choice theory literature, this is known as a minimax winner. Intuitively, policies pi1 and pi2 are trying to generate prompt completions, psi1 and psi2, that are preferred to the generations of the other player. Crucially, because we're not collapsing down the preference matrix to a single reward or utility vector, the minimax winner is agnostic to whether intransitive preferences exist, and therefore will not ignore minority preferences, succumbing to the tyranny of the majority. Unfortunately, computing minimax winners comes with a heavy computational burden. The need to do adversarial training at the scale of LLMs, which is entirely infeasible, both due to compute and memory restrictions. This motivates the key question of our work. Do we actually need two players to compute a minimax winner? We rigorously prove that because of the symmetry of the preference game, we can instead follow a simple and scalable self-play strategy while maintaining strong guarantees. So rather than actually training two separate policies to solve the game, we can instead simply sample twice from the same policy and treat the second set of samples as samples from a fictitious second player. More formally, we propose a general reduction of computing minimax winners to no regret online learning with a single player. Our reduction involves optimizing a sequence of reward functions, each of which sets the value of a completion to be its win rate against other completions from the policy at that iteration. We call this algorithm SPO for self-play preference optimization. In practice, one can implement SPO similarly to reward-based RLHF by first training a pairwise preference model. Then, one samples a batch of prompt completions from the current policy, uses the preference model to compute all pairwise comparisons, and then uses the win rate as a reward for a downstream RL algorithm like PPO. One can also use simpler algorithms like DPO, IPO, or Rebel to approximate the SPO update. If available, one can also use a teacher model to directly provide preference feedback rather than a specifically trained preference model. Please check out our paper for more details, and feel free to reach out over email if you have any questions. Thank you again for your time.